Thanks so much, and thanks so much to all the organizers, especially Juan, for having me here. This is really an awesome place, and I've enjoyed the last week very much, and this week as well. Okay, so I only have some very simple things to tell you today about the Tietze extension theorem in classical reverse math and second order arithmetic, sort of following along from exactly the setup that Tietze described in his wonderful tutorial last week. So let me preface all of this by saying that all my remarks today concern second order arithmetic only, and then tomorrow Sam will give us a higher order perspective on a bunch of related stuff. Okay, so what I want to look at is one more time the Tietze extension theorem. Okay, so this is the version in Simpson's book, RCA, not version of the Tietze extension theorem. Yes, TET henceforth. Okay, so if X is a complete separable metric space, and so since this is so much to write, I'm just going to call this a metric space henceforth, but I'm always thinking, the classic second order arithmetic encoding, again, like Tietze had described, separable metric space. So this is just going to be a metric space henceforth. Okay, so I've got a complete separable metric space that I'm calling X, and then I've got a closed subset of X. This is still the hypothesis, or all the data here. Complete separable metric space, closed subset of this metric space, coded in the negative way, right? Coded in the form of the complement of an open set. Okay, and I've got a continuous function from C to reals, or let's just say, because this is the way that it's formulated in Simpson's book, just to the interval -1 to 1. Okay, so if I have all of this, right, then the Tietze extension theorem says that, well, this function f extends to a continuous function on the whole space x. Okay, so then there is a continuous g, right, on the whole of x, right, again, to this interval -1 to 1, right, extending f, right, meaning that for every little x in this closed set C we started with, that g of x is the same thing as f of x. Okay, so this is the statement that's in Simpson's book, Tietze extension theorem. I guess this comes from Brown, perhaps, originally in his thesis. Okay, so what do I want to say about this? First of all, this is sort of a classic example of some kind of non-trivial mathematics that can be done in RCA not, so that's good. But then let's maybe take another look at what this is saying, right? So this is saying that I'm looking at, in this version, right, a bounded function f, right, where I've given it this pre-specified bound from -1 to 1, right, and I extend it to this continuous g that still respects this pre-specified bound -1 to 1, okay, but the g might not actually respect the true sup and inf of x on the closed set C here. Okay. G, note, G respects the pre-specified bound -1 to 1, right? But it may not respect let's say the inf of the x's in C of f of x, and the sup of the x. Let me draw a picture to really belabor this point, because I was going to anyway. All right, so this is a cartoon situation here. So let's say I've got here my -1 and 1, and let's say this is the, well, I guess, some part of the real line, or let's just say I'm defining my function on 0, 1, right? And maybe my f is defined on a closed set C, right? Kind of looking like this, right? And maybe my f does something like this, right? On C. Okay, so this is a perfectly good f, right? And the theorem says that, well, I can have, let's say if my x is just the unit interval 0 to 1, right? Then the theorem says I have a g that extends f on C and at least respects the -1 to 1 bound. Okay, so my g could do something like this. Colors are too close together. Okay, right. My g could be like this, right? It still stays inside the -1 to 1 interval, but it sort of gets bigger than f and also gets smaller than f, right? Outside of that interval. Yeah. So the g has a bigger sup and a smaller inf than the f does. Okay. Right. Nevertheless, right, it's true that you can choose a g that does respect the true inf and sup of the original f, right? So I could have instead, right, come up with a g that's like this. Okay, and I've preserved not only this pre-specified bound on the range of f, but also the true inf and sup of f. Okay. Right, so this kind of a sup and inf preserving Tietze extension theorem is what I want to look at today, and I want to sort of put this forth as a sort of easy or a snappy example of something that's equivalent to pi11 comprehension. Okay, so that's what the theorem is going to be. Theorem, right? It's maybe a theorem. It's maybe an observation, right? It's maybe just a language trick that we can discuss later. Okay. Right, but the theorem is going to say that in the general like bare space situation, right, a certain way of phrasing the inf and sup preserving Tietze extension theorem is equivalent to pi11 comprehension over RCA naught. And I mean, just to spoil everything, I can tell you what the proof is right away, right? The idea is that, well, finding the sup and inf of a continuous function on an arbitrary closed set is a hard thing, okay? Because, well, maybe there's only complicated points in my closed set, and I have to quantify over all of them, basically, if I want to figure out what the sup and inf is, okay? By extending my f, which is maybe defined only on a complicated set, to a g that's defined like on an easy set, right, on an open set, on the whole space, and it preserves the inf and sup, right? I've changed the problem of finding the inf and sup from quantifying over this complicated set just to quantifying over the rationals of the space. Okay, so so this is this sup and inf preserving Tietze extension theorem that I'm going to phrase in just a second is, in some sense, some kind of rephrasing of finding sups and infs of continuous functions on closed sets. Okay. Right. Okay. So let me now say exactly what I want here. All right, so maybe let me first say, okay, well, let's look at this RCA not version maybe a little more for just a second before I talk about what I want to say for the sup and inf preserving version. Okay, so let's say we're back to the extension theorem again. So let's say I have, again, a closed subset of a complete separable metric space, and I have a continuous f, right, defined on that C to this interval -1 to 1. All right. Okay. And if you just happen to know what the true sup and inf of f are on C ahead of time, right, then you can just use this RCA not version to get a version of the Tietze extension theorem that again preserves that inf and sup. Okay. So if you just happen to know, right, if you know, I'll call this alpha to be the inf of x, c of x, and if you know that some number beta is the supremum of x, c of f of x. You know this, I'll say ahead of time. Okay. Right. Then RCA not by this exact proof, right? Maybe I should say, yeah, the proof here is essentially the usual one, like engineered in RCA not. I'm not going to say anything more about the forward proof of that. Then RCA not can produce an extension G right of f preserving the sup and inf. So with sup, say, of little x in big X of g of x, right, equal to the sup of little x in C of f of x, right, and similarly for inf, right, and this is just because, well, you know these two numbers, alpha and beta, right, so you can scale alpha beta interval to -1, 1, and then do the Tietze extension theorem there, and then just scale back, okay? So just scale -1, 1 to alpha, beta, and back. Okay, so the point here is that to sort of get strength out of some kind of sup and inf preserving Tietze extension theorem, I have to say it in a way that doesn't presume that I know what the sup and inf are ahead of time. Okay, so this is how I want to phrase what I'm going to call the extrema preserving Tietze extension theorem. Okay, so preserving. Extension theorem. Okay, so same input data, right? Let's let C be a closed subset of a complete separable metric space, right? And f a continuous function defined on that closed set. Again, just for convenience, we'll assume everything's at least bounded to begin with, so f will be always a start out with a continuous function to this -1 to 1 interval. Okay, all right, then there is a continuous extension G, right, from the whole space to the same -1 to 1 interval, right? such that, okay, well, first of all, just for propriety, it's an extension, meaning again that for every x in the starting closed set C, g of x tells you the same thing as f of x, okay, right? And then I'm gonna phrase sup and inf preserving as I don't overflow any values of the original function. Okay, so for example, I want to say for every x in the whole space x, there's a y in my closed set C such that g of x is less than f of y. Okay, so for every value my new g can take, my old f can achieve on the original C something at least that big, okay? So this means then that, well, my g can't overflow the f, and therefore my extension g is suprema preserving. This is what, for me, is going to count as suprema preserving. Okay, all right, and then similarly, inf preserving. So for every x in x, there's a y in C such that g of x is greater than or equal to f of y, right? So the g doesn't completely underflow, I guess, the f. And so this would then mean that my g is inf preserving. Okay. Right, so I present this as a not completely unreasonable rendering of the Tietze extension theorem that also says my extension preserves the sups and infs of the original input f. Okay. Right, and then the theorem, just write it here, theorem, observation. Is that the above is equivalent to ACA naught for compact x and is equivalent to pi11 comprehension in general, or for bare space, say. Right. Okay, so I'll explain the proof of this, but it's all very easy. So let me say maybe more. Part of the point here is to maybe also address the sociological question of, say, some real mathematician learns about reverse mathematics and is intrigued, right, and asks you, what are some, give me some examples of things that are equivalent to pi11 comprehension. Yes, Peter. I anticipated this. We're complex mathematicians. Thank you, Peter. Okay, yes, we can. Great. Okay, and I think, I mean, there are good answers to this question, but I would like to propose this as another good answer to this question. Oh yeah, and before I forget, right? Another thing I really like about this is that this came up in Tietze's talk as well, but this his summer school. Yeah, I do not care about how long it takes to prove this. In the summer school, yeah, he pointed out there was this one version of that Ekelin theorem is something about continuous functions that's equivalent to pi11 comprehension, and that's rare and interesting. And this is an even simpler example of the same thing, right? This is a very familiar thing that's just about continuous functions, but still is equivalent to pi11 comprehension in the most general case. So this is another reason why I like this snappy example of something that's just about basic analysis, continuous functions, but yet requires pi11 comprehension. Okay. Right. So for the sociological part of this, again, let's maybe just take a look, since we have plenty of time, at some of the classic examples of things that are provable in things that are equivalent to pi11 comprehension. I think, yeah, I've thought about that. I need to think of the details a little more, but then I think it's still ACA knots. Again, so for this discussion, compact means the usual, uniformly totally bounded definition of compact. I think later on I might mention, I think an interesting situation is, what if your C is not necessarily that kind of compact, but Heine-Borel compact, right? I'm kind of imagining an infinitely branching tree, but the extendable nodes are finitely branching. I think that might be an interesting situation to look at here, but I'll come back to that later if I don't waste too much time slowly writing down things equivalent to pi11 comprehension, which I'm going to do now. Let's see. If C is compact, yeah, you can find the inference loop in ACA knots at least. Yeah. Well, I'm going to show you a reversal to ACA knots, and then you can. Okay. Right. Okay. Some examples. Examples equivalent to pi11 comprehension. So from Simpson's book, right? You've got the Cantor-Bendixson theorem. For metric spaces, complete separable metric spaces. I think this is a pretty good example, right, of something that's equivalent, usual mathematical theorem equivalent to pi11 comprehension. If somebody asks you for an undergraduate theorem, then it's maybe a little bit more debatable. I kind of lost track of what the undergraduate curriculum around these kind of topics are, but do we teach Cantor-Bendixson to undergrads? Okay. So this is a good example, except for maybe if you want an undergrad theorem. Okay, and then there's the every countable abelian groups. Are direct products of divisible groups reduced groups. Which is to say every countable abelian group is the direct product of a divisible group and a reduced group. I guess this is also, yeah? Somebody? No? Maybe I'm just hearing my own echo over here. Anyway, yeah, this is a good example. I think I personally only know this fact from Simpson, but I guess if you're into algebra, this is important. Probably also not an undergraduate theorem. I think at least for me, I only learned about finite groups when I was an undergrad. Okay, so then there's more like descriptive set theory kind of stuff, which are good examples for us, but maybe not for our a real mathematician. So there's the classics sigma 0, 1 and pi 0, 1 determinacy. Okay, and then there's the delta 0, 2 or arithmetical Ramsey theorem, like Galvin-Prickery. Okay. Again, yeah, these last two I think are great examples for us, but maybe not great examples for everybody. And then sort of a smattering of further examples. Okay, so there's some technical enhancements. This is kind of a personal list, so maybe other people have better additional examples to shout out. Okay, so technical enhancements.
You can make that equivalent to.
Okay, great. You can tell us tomorrow.
Yeah.
Yeah. Okay, so technical enhancements of some countable graph theory stuff, in particular Kernig's duality theorem, and Menger's theorem. By technical enhancements, I mean sort of the textbook proofs prove more than the bare statement, and that more gives you something equivalent to pi11 comprehension. Kernig's duality theorem, as stated, is equivalent to ATR naught, and Menger's theorem somewhere between ATR naught and pi11 comprehension, but not pi11 comprehension itself. Okay, and then Anton has a bunch of great work on the well order preserving principles direction. So I'll just say dilators have certain fixed points. Okay, so this list came from slides from a year ago, so by now I certainly have no idea what this means anymore. So if you want to know what this means, ask somebody from Ghent. But I think pretty clearly not an example for our mathematician friend. And then here's a recent one from Giorgio that I really like that comes from the study of second countable spaces, like in Demir's great tutorial. This is every countable, second countable T3 space. This is another like a decomposition kind of thing. Is a disjoint union of a scattered space and a space homeomorphic to the rationals. Okay, again, good recent example from Giorgio that I like. Okay, and then there's this echelon variational principle that Tietze mentioned in his tutorial. Okay, and for all of these, as an example of what I'm trying to talk about, there's things to like and things to not like. This last one, for example, it's not exactly an undergraduate theorem, and also, like, even though I worked on it, I'm not 100% confident I can write down the statement correctly because I always mix up the inequality. Okay. Right. And again, with this statement here, right, there's stuff to like about it and stuff not to like about it, right? I think it's pretty defensible as an undergraduate theorem, right? But also it's kind of this specific sort of phrasing in such a way as to get the theorem that I want in the end. I mean, maybe a little artificial for that reason. Okay. So I'll try to do a reversal for this ACA compact statement, and then you can see if I messed it up or not, because I guess you're suspicious now. Okay, so this is very, very silly. Reversal, maybe? Okay, so let's have a descending sequence of rationals in the unit interval, right? And the monotone convergence theorem, right? Finding the limits of the sequence is a classic thing that's equivalent to ACA knots, and I want to try to use my compact extrema preserving Tietze extension theorem to figure out the limits of this thing. Okay. Yeah. Oh yeah, we've got the shadow. Yeah, sorry. Good. Now what? Somebody wants it back down? Peter? Yeah, okay. Use the hook when I have a chance. Okay. This general life advice from Peter. I'm not willing to say on that. Okay. Wasted half of my time so far. All right. Okay. Yes. Yeah. Great. Sorry. Yeah. Thanks. Okay. And the goal is to show that the infimum of these guys exists. This is a classic thing equivalent to ACA knots. ACA knot. All right. I'm gonna let X, like my ambient space, be just the unit interval, right? Counts as compact in the sense of uniformly totally bounded. Okay. Right. And I'm going to let my C be this interval, right, that I'm going to write this way, right? It's going to be the interval from 0 to the inf. Okay. Right, and I claim this counts as a closed set because I can enumerate the complements, right? What's the complement? Well, it's everything that's bigger than any of these A's, right? So the complement is enumerated by this collection of intervals. Okay, so far? This is extremely silly. And now I want my function to be just the identity restricted to C. I guess, yeah, just is the identity restricted to. Okay, right? And if you, so I guess I don't really care about is do I have this function coded in a way such that the domain is exactly C? But you could cook up a code that does that if you wanted. Like I'm okay with saying, either I have the code for f on the whole unit interval, and I'm just gonna look at the points that are in C, or I'm actually gonna recode f in such a way that its domain is exactly this closed set C. Interchangeable, either way is fine. Okay, so now let's let G be an extension, and in fact a soup preserving extension. right? Be a soup preserving extension of f. Yeah, just of f. Yeah, so soup preserving extension of f. I guess maybe I should write this more clearly. Rewrite this first attempt. All right, so what I really mean here is let G I guess yeah, this is since it's this function f is to the 0, 1, so also -1 to 1 interval. Be a soup preserving extension f. Okay, right. Okay, so since G is a soup preserving extension of f, I can sort of approximate the supremum of G and therefore the supremum of f from below just by evaluating G on the rationals, right? And okay, so the right, and the soup of f being the soup of f is the imp that I'm looking for, right? And I can approximate that from below by evaluating G on the rationals, whereas it's naturally already approximated from above, so I can zero in on this number. Approximate this inf from below by evaluating G on, let's say, 0, 1, 2, and naturally approximated from above, so I more or less have the Dedekind cut here for this, and I can give a Cauchy sequence approximation. That's the idea here. But
compactness of C implies already the existence.
C is I guess perhaps not. I can't. Well, yeah. So I guess I'm only claiming compact. Yeah, I guess that's right. Yeah, I'm only claiming that the X is compact. Yeah. Yeah. Okay. Yeah. Good. That's a good point. So yeah, you're happy with this? Good. Yeah, passes the Alberto test. Good. Good for me. Okay. Yeah, I guess so. Yeah, because right. Yeah, because compactness here means uniformly totally bounded. So you would have to be able to come up with you have to essentially be able to come up with this point, I guess. Yeah, to give the give those bounds. Okay, right. So I think Alberto says this is okay, and I think we can all agree it's very silly, right? This argument. All right. So maybe more interestingly, let's take a look at the pi11 comprehension reversal. It's less silly, but still very easy. Hook. You didn't like booby trap this overnight, did you, Peter? Thank you. Okay, oh, now we need to mess this all up. Sorry, give me a minute. I'm not doing this efficiently. I don't have anything interesting to say while I'm cleaning the board here. Also, it's taking some concentration. But I will do a second one in preparation. I guess I could narrate cleaning the board. Entertaining, everybody. Erase this one ahead of time in case we need it. Yeah. Okay, so I guess maybe one thing I can say is that for the next reversal, really what I want to consider is the statement that says, the extrema preserving Tietze extension theorem holds for all metric spaces, which means I can use this ACA naught reversal we just did to bootstrap to ACA naught. So I'm going to work over ACA naught for the remainder here. Over I11 comprehension reversal. And over ACA naught, because we bootstrapped up to it. Okay, right, and the classic thing here is from Marconi, right, which says that if T is an ill-founded tree, so if T has any path at all, then T has a leftmost path. Okay, so that statement is equivalent to I11 comprehension, right? Is one of the classic tools of reversing to I11 comprehension. So it is equivalent to I11 comprehension, right, over RCA naught. So this is what we're going to base the reversal on. Okay, so let's let X, and this time my space is going to be bare space. Okay, and my closed set is going to be just described by some given ill-founded, the path through some given ill-founded tree that I want to find the leftmost path through. T is going to be the path through T, right? Some ill-founded tree. Okay, and now my function is going to be this one. -1 to 1 or 0 to 1, right, given by. So I'm gonna write down here a somewhat inscrutable formula, and then I'm gonna draw a picture explaining what this function is doing. Okay, so this function is gonna send. Again, this is a function that's defined on all of bare space, but I'm just considering its restriction to the path, to my C here. Okay. This function is this one here, minus. So So that the x here is a point in Baire space, so I'll index into it in the usual way. So 2 to the minus x0 minus 1 plus 2 to the minus x0 minus x1 minus 2 plus, right, and so on. Maybe I'll do one more term here. Plus 2 to the minus x0 minus x1 minus x2 minus 3, and so on, right? In general, right, this is the sum over all the n's of 2 to the minus x0 minus x1 minus x2, right, etc., out to minus xn, right, in the nth term, minus n minus 1, right, add up all of the stuff like this. Okay, what is this? What is this doing, right? I'm looking at, right, the unit interval here, 0 to 1, right, and I'm chopping it into intervals, say, halfway here, and halfway here, and halfway here, right, and so on, like the intervals of size 2 to the minus n. Okay, the first position of little x tells me which of these intervals to go in. So like x0 equals 0 says go here, right? x0 equals 1 says go here, right? So over here go sequences that start with a 0. Over here go sequences that start with a 1, right? And so on. And now I do the same thing inside each of these intervals, right? So again, this is going to just look the same, but then I do the same thing, right? Cut this first interval again into intervals of, size half as big each time, right? And then sequences that start 0, 0, right, go here. Sequences that start 0, 1, go here, right? And similarly for all of these intervals, right? So sequences that start 1, 0, go here. Sequences that start 1, 1, go here, right? And so on, right? And that tells me. So this is what my function does. Okay, it's this idea. Hopefully it's clear enough what this is doing. Okay. X is Baire space, yeah. And to the. And so. Yeah, okay, so like, yeah, great. So this like sequences that start 2 go here in this interval. I could, yeah, and so on. Yeah, sorry, this was a very, misleading labeling. Yeah, sorry. Okay, yeah. And then down here would be like, what goes in this is sequences that start 0, 2, etc. Okay, and of course the point is that the lefter my path is, the righter the output is, yeah? Okay. So let me just, okay, we're running out of time here. So x is to the left. This is just informal, but I think you know what I mean. To the left in Baire space, right? That corresponds to f of x being to the right in the unit interval here. Okay. Okay. So finding the leftmost path in my tree, right, is sort of reflected over here as finding how far right can I go, right? So what's the sup of f of x on my closed set? Okay, and we're going to figure that out by doing a sup preserving extension of f to my whole space, right? And then it's easy to extract what the sup is from what I said before, right? If I've got now calculating a sup on an open set, right, you can just do that in ACA naught, and I've bootstrapped to ACA naught. Okay, so let's G now from all of bare space to, I said 0, 1, right, whatever. It's changed from -1, 1 to 0, 1. Be a soup preserving extension of F. Okay, and we can use ACA naught to get now some number I'm going to call B, right, which is the supremum of G on all of bare space. Okay, right, which because G was soup preserving, right, it's the same as the soup of F on the original C. Right, soup of X, C of F of X. Okay, so you get this number B somewhere on the number line here, and then you can sort of retrace through this procedure to see what path it corresponds to. I won't. I'll just say you can do that. You can imagine how this works. Okay, so then use, or just use B to extract leftmost path through T. Okay. Sorry, my handwriting is very deteriorating rapidly. Approach some singularity in like 7 minutes here. Okay. Oh, great. I'll emphasize again, this is a easy example of what I said it's an example of, right? Something about continuous functions equivalent to pi1 comprehension, right? Easy in the sense that it's both a some certain phrasing of a well-known theorem, and also the argument is very easy as well. I'll say this is, of course, very closely related to the statement that a continuous function on a closed set has a sup and an imp, right? That's also equivalent to pi1 comprehension, right? And you can give the same kind of argument to show that. That statement itself, I wouldn't really call a good example of something equivalent to pi1 comprehension for our mathematician friend from the beginning, because it's not really a theorem, right? To a real mathematician, right? That it's the range of a function or something is just irrelevant, right? It's this set of real. So the theorem is just the completeness of the real line. But we can, through this, what I said might be a language trick, just express exactly that thing in the form of something that is called a theorem to most everybody. Okay, so the very last thing, if you let me, I think I do this in 5 minutes, modulo. Let me erase the board again. So I think, by now, I think we're well past the point of the idea of there being any one true strength of a theorem. So I want to just maybe recall various different versions of the Tietze extension theorem and where they fit in the big five.
Not out of this world to say, well, there is no.
Right. So, as I said, we're past the idea of a theorem having any one true strength. And again, yes, we all expect you to comment on this further tomorrow, Sam. Will be good. Okay. So Tietze extension theorem in the big five, just really quick. So RCA naught we've got the, I'll just call it the vanilla Tietze extension theorem from the beginning. Okay, so weak Kernig's lemma. There's this sort of technical version that says, well, if I'm in a compact situation and I know the modulus of uniform continuity for the input function, which I've been calling f this whole time, then there's an extension where you also have the modulus of uniform continuity. So I'll just call this uniform continuity preserving Tietze extension theorem for compact, I'll just say compact X. I think X equals unit interval is also good. ACA not, right? This is what we just said here, the extrema, Alberto approved extrema preserving Tietze extension theorem for compact X. Okay, and then I'll tantalizingly leave a gap. Then pi11 comprehension, what we just showed here, extrema preserving. God, sorry, preserving Tietze extension theorem. Okay, I'll just clarify that it's non-compact situation for a bare space. Okay, so now what about ATR not? So this is something I'm still thinking about and haven't really just had the time to work this out completely. But kind of like I was hinting at earlier, you might be able to say something about extrema preserving Tietze extension theorem on Heine-Borel compact spaces here. This is a bit speculative, but yeah, or maybe I should say ongoing work. Preserving Tietze extension theorem for Heine-Borel compact X, and so far this is over some kind of choice. I need some kind of, so far it's some kind of Tietze theorem to make this work. So at least maybe at least over some kind of sigma 1,1 AC, which is still technically a reversal, but not a very not as satisfying as over RCA not or something. Yeah, maybe something can be done here as well. But so next talk, maybe I'll have more to say about this. Thanks so much, everybody.